how user-friendly.
Okay, so we are talking about increasing, decreasing functions, and we're going to get into max and min function, where functions have maximum and minimums. But I wanted to go over one example of f of x equals ln of x, and I forgot to start the recording. And so we already worked through this, but I want to just kind of walk through it. And so you should be able to see on my screen, and I'll let me zoom in a little bit. Maybe. Okay, so we are looking at f of x equals ln of x, and we're trying to find where it's increasing and decreasing. And when we're looking at where a function is increasing and decreasing, the first step is take the derivative of the function. And so we took the derivative of natural log of x and found that it was 1 over x. Once you find the derivative, you're looking at when is the derivative equal to 0 and when is it undefined. And so looking at this, we set 1 over x equal to 0. But found that when we were solving for x, we got 1 equals 0, which is a false statement, which should clue you in that there's no solution for that equation. But we also want to look at when the derivative is undefined. And so looking at 1 over x, we can see that it is undefined on values which set the denominator equals 0, which in this case is 0 itself. And so those are called critical numbers or critical values. If your value is undefined for the original, that kind of helps things. And also looking at domains, if your domain is limited for the original function, it's kind of helpful also to see that. So we kind of reviewed what the graph of y equals ln of x looked like, and that by definition, that the domain, you can't take a natural log of a negative number. And so whatever you're taking the natural log of had to be greater than 0. And so in our case, x had to be greater than 0. We plotted a couple of points to, again, review what our y equals ln of x looked like. And we saw that it was strictly an increasing function. And again, we saw that, and we also had an asymptote at the y-axis. But just to show, because maybe we didn't graph this and we wanted to do this just by taking derivatives. So we found our critical number, which was 0, where it was undefined. And so we needed to plug in a number, usually on the left and the right of the critical number. But I only chose the right because I know x less than 0 is not part of my domain. And so it's not either going to be increasing or decreasing if that's not part of my function. And so we just chose any number that was bigger than 0, and we just happened to choose 1. And if you plug 1 back into the original, you get back 1, which is a positive number. So a derivative of a number and it's positive, that tells us it's increasing there. And since there was only one critical number, then we can say it's strictly increasing on that interval to the right of 0, which is 0 to infinity, not including. And so that, we just finished that, and we're going to look at one more example from the homework right now. And I'm going to pull in, and I just pulled up my math lab. So I'm going to pull in the first question of 5.1 for my math lab. Just pull this screen over. Thanks. Okay. Okay, so I'm going to go 5.1. I believe I thought I already pulled it in, but let's do it again. 5.1. I'm going to look at preview. Okay, so it says suppose the graph below is a function of f prime of x. And so that's where I was like, we got to remember that this is the derivative function and not the original. So, so the graph below is f prime of x, the derivative of the function f of x. Find the opening in the interval where f of x is increasing and decreasing. I'm not sure if I can write on this or not. And so, no, I can't write on that screen, but I know what I can do. So that snippet tool, I don't know if I showed you guys, but if you have the snippet tool, you can go anywhere and you can highlight and snip and paste. So I'm going to just do that. So I just saved it. I'm going to put it on a Word document. Okay, so now I can write. Okay, so the key thing here is that this was the derivative. And so if f prime of x, remember we plugged in a number and it was less than 0, it told us that f of x is decreasing there. And so if we looked at f, the derivative, and we plugged in a number and we saw that we got a positive number, then it told me that our original function f of x is increasing. And I don't know if you guys kind of remember the first part, first test, I think we actually even looked at kind of graphing the derivative function. And so if we have the derivatives of less than 0, and this is f prime of x, so notice that this piece under here, this is falling below the x-axis. And so these are the values where f prime of x is negative. And so I can say that f of x is decreasing and so I'm going to look at the x values where it starts to go below the x-axis. And so I notice that is when x is -6. I'm not including because that's when it's 0. That's actually giving me either a max or a min. And then it's stopping at x equals -1, but not including union. And then it also falls below the x-axis when x is 1, but not including, to x equals +6. So again, this is my derivative function. And so to find out where my original function is increasing, I'm looking at when is my graph falling above the x-axis. And so and I'm only looking at the x values where that is occurring. Oops, don't look at that. And so the x values where that is occurring is anything that is less than -6. So I know my derivative function has positive values when it's above the x-axis. And so this is from -infinity to -6, not including, union. Then it's also above the x-axis from -1 to 1. Union, it's also above the x-axis from 6 to infinity. And so this is where f of x is increasing. Okay, so the key on that again was noticing that it was talking about you were looking at the derivative function and not the original function. Okay, so actually this kind of ties into what we're doing next in 5.2, and we actually kind of talked about it a little bit about finding absolute or local max and local mins. If let's just kind of look at our number line real quick and see if we, from our derivative function, can tell where our max and where our mins are going to be from that last example. And so if I look at the number line, Oops. And I look at the places where it's crossing the x-axis. We saw that that happened at -6. We saw that happened at -1, at +1, and at +6. Oops. I don't know if I can go back down there. Let's just undo that. Nope, that doesn't work. Okay. There's our number line. Let me just play with this a second. And so we saw by looking at the graph of the derivative that it was decreasing or increasing from -infinity to -6. And so we know it's going up. So I'm going to just write part of my graph going up from left to right. We also saw that it was going up from left to right from -1 to 1. So I'm just going to put an arrow up left to right. And also is going up left to right from 6 to infinity. But if I looked at where the graph with f of x was decreasing, we looked at and saw where it was falling, the derivative function fell below the x-axis between -6 and -1. So our graph is going down left to right in there. And the same thing, from 1 to 6, our graph was decreasing. These were values where f of x or f prime of x equals 0. So these are sometimes max or mins. And we can look at our case. And if we look at it and we got something that's increasing to decreasing, oops, I wanted to do that. So we got something that increases, right? And then it goes down and it decreases. We can kind of see that that right here, right, is going to have to be a max at x equals -6. Or if we have something that decreases and then starts to go up to increasing, come on. Right there, that's going to have to be a min. Or increasing to decreasing looks like a max. Increasing to decreasing. So we can see where the peaks are based off of where it's increasing and decreasing. Where the values over here, these are going to be min at x equals -1 and x equals 6. Oops. So this was x equals -6 and x equals +1, or where the max and where the mins occur. So basically all we're going to be doing is what we just did here, is we're going to look at our functions. It's going to ask us to find where relative, they might say relative or local max or mins occur. And so we're going to look at the derivative, find where it's 0. And then we're going to test values on each side to see if it's increasing or decreasing. So let me just kind of show you a graph real quick. So it's possible that you find a critical number when you took the derivative. So let's say you had some graph like this. So if this is f of x, well, just looking at the function, I can tell that it's increasing everywhere. But if I hadn't graphed the function, I didn't have the graph of the function, I wouldn't know that. But if you look at this, there's actually a point in here where f prime of x, our derivative, is equal to 0. But notice that on the left and the right of this, it's f prime of x is positive because it's increasing. And so here's a point where you have a critical number, but it's neither a max nor a min. So here's where a critical number is neither a max or a min. Okay, so that's a case where it's really important why we have to test on the left and right of our critical numbers to see that it's changing direction, either from increasing to decreasing or decreasing from increasing. Okay, so let me pull out an example. Make that bigger. It might be faster if I just type it. So find the x values of all points where the function defined as follows have any relative extrema. Find the value or values of any relative extrema. Okay, so just again, terminology, that relative extrema, it's just asking you to find local max and local mins. So we want to find the local max and min points. Okay, so we need an equation. So let's say f of x is equal to x cubed plus 3x squared minus 24x plus 2. I'm just going to change that to a little f of x because later on in the course, big f of x is going to represent the antiderivative and not the derivative. Okay, So again, first step, we want to find the derivative of f of x. So again, I'm starting you guys out easy. So hopefully by now, this derivative is a piece of cake. So taking the derivative of x cubed, using the power rule, we have 3x squared plus derivative of 3x squared, bring down our power. So 3 times 2 is 6x. Derivative of negative 24x is minus 24. And derivative of a constant is 0. So we're looking at when is f prime of x equal to 0? And undefined. In this case, this is a polynomial. There's no values where f prime of x is undefined. And so we're looking at when is 3x squared plus 6x minus 24 equal to 0. When I write that out, I'm going to factor out a 3. So pulling out a 3, that would be 3 times the quantity x squared plus 2x minus 8. We're looking at when that is all equal to 0. So this is a quadratic function. So I'm looking at, can I find two numbers that multiply to negative 8 and add to 2? If so, I'm going to factor it. If not, I would use my quadratic formula. And so there are two numbers that multiply to negative 8 and add to 2. And that would be positive 4 and negative 2. So x plus 4 is one factor and x minus 2 is another factor. So once you factor completely and it's set equal to 0, set each factor equal to 0, well, it's impossible. 3 can never equal to 0. If there was a variable out here, we could have that. We're looking at when is x plus 4 equal to 0. You can see that's x equals negative 4. And we're looking at when is x minus 2 equal to 0. And that is when x is equal to 2. And so we just found our critical numbers. X equals negative 4 and x equals 2. Okay, so we got a test to see if these are actually max or mins. And so putting these numbers on the number line, we want to choose some number on the left and we want to choose some number on the right. And we're plugging this back into our derivative function. It's possible if you wanted to plug it into the factored form. Again, all we're really worried about is our derivative at the number to the left or right, positive or negative. And so technically we could just kind of use some logic. If we plug it into 3 times the factor x plus 4 times x minus 2. So let's say we plugged in x equals negative 5. So if I plug that in to my derivative function, I mean, these aren't bad numbers at all, but I can see that 3 is a positive number, right? All times negative 5 times 4, which is a negative number. All times negative 5 minus 2, which is a negative number. And so if we think about it as multiplying positive and negatives, well, if I multiply 2 negatives and a positive, I know that this is greater than 0. And so this piece must be increasing here. And so again, you want to choose a number now to the right of negative 4, but to the left of 2, so in between negative 4 and 2. So choose any number. And so if we chose, let's say, x equals, well, 0 is in that interval, that's always the easiest. So if we plug in 0 into the derivative, well, 3 all times, well, 0 plus 4 is 4, 0 minus 2 is negative 2. And so I can multiply that out, or I notice that this is going to be less than 0 because I'm multiplying two positive and a negative. And so if that's less than 0, derivative is less than 0, then that tells me my graph is decreasing within this interval. And so one more number, I need to choose something to the right of 2. And so choosing a number to the right of 2. So let's say x equals 3. And we plug that into the derivative. That's 3 all times 3 plus 4 and 3 minus 2. Oops. So positive times positive times positive is equal to a positive, which is greater than 0. So this tells me it's increasing. And so just based off of that, I can tell that I have what type of point at x equals -4 and what type of point at x equals 2. And so at x equals -4, well, this was increasing and then it went down to decreasing. So x equals -4 is where a max occurs. And then if I look at x equals 2, well, to the right of 2, it was decreasing. And then at 2, it changed direction and then it started to increasing. And so from decreasing to increasing, then I know a min occurs. Okay, so these are the x values that occurs at. And again, I think I mentioned this last week, is that they're going to actually want the y value that these occur at. And so to get the y value, we need to plug these x values back into our original equation. So I'm going to go back and see what that original was. Okay, so to find what value the maximum and minimum are, plug the x value back into the original function. So in our case, I just rewrote it there. F of x was this. So if I look at f of 4, this would equal 4 cubed plus 3 all times 4 squared minus 24 all times 4. And it's not 4, it's -4. Okay, so this case, we actually need to know what the x and the y values are, or we need to know what that value is. It's more than just is it positive or negative. So -4 cubed plus 3 times -4 squared, which is 16, minus 24 times -4 plus 2. So I get that this is 82. Okay, so we have a max value of 82. And so to find the min value, we know it occurs when x is 2, but we don't know what the y value is. And so the minimum point that this is going to occur at. So plug in 2 wherever you see an x in the original. So 2 cubed plus 3 all times 2 squared minus 24 all times 2 plus 2. And so we got 2 cubed is 8. 4 plus, so plus 12 minus 48 plus 2. So this gives me negative 34. So we know that the min value occurs of negative 34. Okay, so any questions? Maybe, let's see. Okay, so right before break, we were going over a problem and I put in something wrong into the calculator. So you want to just make sure that when you plugged in 2 that you got back negative 26. And so the minimum value when x equals 2 occurs at negative 26. And so we're just looking at some more problems, doing the same thing where we're finding the local extrema or relative extrema. Depends on what book and how they define it. And I moved my book aside, so let me grab that real quick. Okay, so let's look at starter. I don't know why it's doing that. Let me try one more time. Okay, so we're looking at f of x, and I'll go back and plug in f of x in a second, is equal to x squared minus 2x plus 1. And that is all divided by x minus 3. And so same idea, we want to find out where the local extrema occur. And so we're going to do that by finding critical values. And so if you look at this, I can see right now that our domain of f of x is limited. We can't have x equal 3. So notice x cannot equal 3. And we want to take the derivative. And so taking the derivative, I notice that we need to use the quotient rule. And so using the quotient rule, I need to take the derivative of the numerator. So derivative of the numerator, x squared minus 2x plus 1 is 2x minus 2, all times the denominator, which is x minus 3, minus the numerator, which is x squared minus 2x plus 1, times the derivative of the denominator, which is 1. All over the denominator, x minus 3, quantity squared. Okay, so looking at that, I need to clean it up to figure out when is that equal to 0. So I'm going to expand by distributing 2x minus 2, that quantity, to x minus 3. And so 2x times x, that gives me 2x squared. 2x times negative 3 gives me minus 6x. And then negative 2 times x is negative 2x. Negative 2 times negative 3 gives me plus 6. And now we need to distribute that negative outside of the parentheses in the numerator. And so distributing the negative, we get negative x squared plus 2x minus 1 all over the denominator squared. So combining like terms, looking at all my terms that have x squared in them, I have a 2x squared minus a 1x squared is x squared. Looking at all my terms with just a single x, I have a negative 6x minus 2x is negative 8x. Negative 8x plus 2x, so that gives me minus 6x. And then I have positive 6 minus 1, so this is plus 5, all over my denominator, x minus 3 quantity squared. Okay, so we're looking at now, when is f prime of x equal to 0? So, or undefined. So if we set this whole thing equal to 0, notice that anytime you have a rational function and you set it equal to 0, only values which is going to set this whole thing equal to 0 is the numerator. Because if we multiply both sides by our denominator and we multiply the denominator on the right, which is 0, that's always going to cancel out and gives us back 0. You can write in there, but if we look at multiplying both sides by x minus 3 quantity squared, because it's an equation, if I do something to one side of the equation, I got to do it to the other side. The whole point of that was so the fraction went away on the right-hand side of our equal sign. And so we have, if it's okay, can we factor this at the same time? What's inside? So I noticed that x squared minus 6x plus 5 can be factored. There's two numbers that multiply to a positive 5 and add to a negative 6. So negative 5 and negative 1 multiply to a positive 5 and add to a negative 6. So our factors will be x minus 5 times the quantity x minus 1. So I can see right away my critical numbers. Well, it's when x minus 5 equals 0, so it's when x is 5, and it's when x minus 1 is equal to 0, so it's when x equals 1. But we also have to look at when is this undefined. So x minus 3 can't equal 0. Can't have 0 in the denominator. So x can't be 3. So that's also considered a critical number. Sorry. Okay, so now we need to test intervals left and right of our critical numbers to see what's going on. Before we do that, let's go back up to our original function. Do you guys know what's happening when x equals 3? So recall graphically, if you have a rational function, values which set the denominator equals 0 and not also the numerator were vertical asymptotes. So back up here when x couldn't be -3, x equals 3 is a vertical asymptote. So I know that x equals 3, since it's a asymptote on my original function, x equals 3 is not going to be a local extrema. But if they were asking me where it's increasing and decreasing, I need to know that anyways. But just keep that in mind when we're finding what's happening on the left and right of these critical values. And so plotting our values, I have 1, I have 3, and I have 5. And I just put a note to myself to remind me that that was a vertical asymptote. And so remember, we're plugging these back into the original function, not the original, the derivative function. And so our original function, if you want to, again, you can keep it as factor form, or you can keep it as x squared minus 6x plus 5. Again, if you use it in factor form, you can think about multiplying positive and negatives. And notice our denominator of the derivative, that's x minus 3 quantity squared. So notice any number that we plug into the denominator, it's always going to be a positive number. Okay, so choose a number to the left of 1. And so let's say we chose x equals 0. If we plug it back into the derivative to see if it's positive or negative. Well, if you plug in 0 for x, you're going to get -5 all times -1 in the numerator, all over -3 quantity squared. So I notice that this is greater than 0. And so since that value is greater than 0, then I know on the left of x equals 1, my function f of x is an increasing function. So same kind of idea, we're going to multiply on the right, or we're going to plug in a value on the right of 1. And so let's plug in x equals 2. So plugging in 2 wherever we see an x in our derivative function. So we have 2 minus 5, all times 2 minus 1, all over 2 minus 3 quantity squared. So if we do that, we get -3. 2 minus 5 is -3, all times 2 minus 1, which is 1, all over -1 quantity squared, which is 1. So that's equal to -3, which is less than 0. So that tells me my graph is decreasing between +1 and 3. Okay, so it's an asymptote at 3, but I want to see what's happening on the right-hand side of that vertical asymptote. So choose a number to the right of 3, but to the left of 5, so in between. So if we chose x equals 4. And so plugging that into our derivative, we have 4 minus 5, all times 4 minus 1, all over 4 minus 3 quantity squared. So 4 minus 5 is -1. 4 minus 1 is 3. All over 4 minus 3, so that's 1 squared is 1. So this gives me back -3, which is less than 0. And so on the left-hand side of that vertical asymptote, it's also decreasing. And so one more number I need to choose. So let's say a number bigger than 5, so let's choose 6. And again, we're plugging that into our derivative function to see if it's positive or negative. Okay. So f prime of 6 is equal to 6 minus 5, all times 6 minus 1, all over the quantity 6 minus 3 squared. So that's all. 6 minus 5 is 1, 6 minus 1 is 5, so 1 times 5, all over 6 minus 3 is 3, and 3 squared is 9. 5/9 is bigger than 0, and so I know on the right of 5 that that is increasing. And so looking at this, I can see that x equals 1 because we have something that is increasing to decreasing. That x equal 1 is going to be a max. And then 5, because we have something which is decreasing to increasing, I can see that x equals 5 is going to be a min. So x equals 5, I'm sorry. At x equals 1, we have a max. F of 1. And at x equals 5, a min occurs. At the value f of 5. So you got to go back to the original function, plug in 1, and figure out what you get. And I got to go back to the original function. Oops, sorry. Uh-oh, sorry about that. Camtasia starting. I accidentally pressed a button on the bottom of my toolbar. Doesn't have the X on it. Can you guys still see my screen?
Yeah.
Okay. Let me turn off that Camtasia. Sorry. Okay, I can't figure it out right now. It might pop up in a second though. So let's look at f of 1. So if we plug in 1 there, we get 1 squared is 1 minus 2 plus 1 all over 1 minus 3. And so that what gives me 0 over -2, which is equal to 0. So our max occurs at x equals 1 and gives us a value of 0. And if we plug in 5, so we have 5 squared is 25 minus 2 times 5, so minus 10 plus 1 all over 5 minus 3. So this gives me 15 plus 1, so that's 16 all over 2, which is 8. So this is giving me a min value of 8. Okay, so how can I have a max value when y is 0, and then a min value of x equals 8? Did I make a mistake? Why or why not do you think that? So my max value is sitting lower than my min value for y values. So let me see if I can move this. Okay, well, thank goodness I know I didn't do anything wrong. But I think it's a good question, because if you didn't know what was going on, you might think you did something wrong. So notice, if we look at it, our asymptote, we have an asymptote in between. And so it's like our graph is divided in between those two, right? And so you have to pick up our pencil and start all over again. I'm wondering, it could be cool if we could, which we probably can. Let's go over to possible. Let's go to Desmos. And let's graph what we had of f of x. Okay, so notice that we saw that x equals 1. We had a maximum. And our y value was 0. And you can see that I'm highlighted that max point there at 1, 0. We also saw that there was a min value when x was 5. And that min value, our y value was 8. And if I zoom out a little more, you can notice that there's an asymptote at x equals 3. There's no graph that's, as x approaches 3 from the right, this is a kind of reminder of limits, it's going to positive infinity, and as x is approaching 3 on the left, the graph approaches negative infinity. Any questions on that? Okay, so maybe one more. You guys want E or natural log? Here, let's do the E. Unless I got a comment. And so, we're given that f of x is equal to 3x times e raised to the x plus 2. So same directions as before, figure out where your relative extrema occur. So here's a case where we have to use our product rule when we take the derivative. Okay, so let's take the derivative of that. And so if I look at the derivative of 3x, I know that this is 3 all times the derivative, or sorry, not the derivative, of the function itself, ex, plus the first, which is 3x, times the derivative of e to the x, which is e to the x, plus the derivative of 2, which is 0. And so we have 3e to the x plus 3x e to the x. And we want to know, when is this equal to 0? Okay, so notice that we can factor this. We have something in common with both of those terms. So notice we have a 3 in common with both terms, and we have an e to the x in common with both terms. And so we can pull a 3 e to the x out of both of those. And if I pull a 3 e to the x out of the first term, I'm just left with a positive 1. And if I pull a 3 e to the x out of the second term, I'm just left with an x. And set this equal to 0. Okay, so it's completely factored on the left. And so I'm looking at, when is 3e to the x equal to 0? And I'm looking at when 1 plus x equals 0. Okay, so that second equation is much easier. So I can see that that's x equals -1. That first equation, it's a little bit harder, and if you don't understand how to solve exponentials, or you don't know what the graph of 3e to the x is, it could be more difficult. So to graph or to solve exponential equations, basically you would isolate the exponential piece and then take the log or natural log of both sides is one way to do it. But I know, if you recall, or if you look at the graph of y equals e to the x, basically that is a graph that falls above the x-axis. It's getting closer and closer to 0 as x goes to -infinity, but never touches. And multiplying that by a constant of 3 just makes it grow faster. So that 3 is not making it equal 0 ever by multiplying. And so right here, this is impossible. If you divided by 3 and took the natural log of both sides, you would have had to take natural log is 0, and if you plug that in the calculator, you're going to get an error. Again, showing you that is not possible. Okay, so we only have one critical number. This is defined. We also, for our critical numbers, look at where it's undefined, but our function is defined everywhere. Our derivative is defined everywhere for the domain. And so x equals -1. This is our critical number. Which is kind of nice, because that's telling me I only have to check 2 different regions. X equals -1. So looking at the derivative and plugging in a number to the left and the right. And so if we plug in -2 into the derivative, so what was that? 3e to the -2 all times -2 plus, 1 plus -2. Again, I'm really only curious, is this a positive or a negative number? I know e to any number is always positive. So this is a positive number, or you can use your calculator, and 1 minus 2 is -1, so that's a negative number. So if I multiply a positive times a negative, I know that that's a negative number. It's smaller than 0, and so it has to be decreasing to the right of -1. So choose something which is bigger than -1. And so if we chose 0, which is our easiest case, so let's say x equals 0. and we plug it into the derivative function, we get 3 times e to the 0, all times 0 minus, I'm sorry, 1 minus 2. No, let me say that one more time. I'm trying to do too many things at once. We're plugging in 0 for, and I'm still trying to do too many things at once. We're plugging in 0 wherever we see an x in our original, in our derivative function. So we have 3 e raised to the 0 power, and then we have 1 plus 0. There, I did it. This is equal to, well, e to the 0 is 1, and that 1 times 3, so that's 3, all times 1, which I can see is positive. You can see it's 3. It's greater than 0, and so I know it's increasing on the right of -1. So something that is decreasing and then increasing, looking at it, we can tell that we're going to, we can tell that we're going to get a minimum value at x equals -1. So min occurs when x equals -1. And we need to figure out what the y value is there. And so we need to plug that back into our original. Okay, so let me plug that back into the original. Let me grab the original again. So f of -1, this is equal to 3 times -1 times e raised to the -1 plus 2. So that would give me -3 e to the -1, that brings the e down to the denominator. So at -3 divided by e, and then plus 2 outside. So that gets me approximately 0.9. Okay, so the min occurs at 0.9. So that's our min value. So any questions on that? Any questions in general?
This was 5.2, right?
This is 5.2, correct. 5.3 is really not bad at all, guys. Basically, it's just taking what we're doing right now and using the second derivative test. So basically, we're gonna take a derivative twice instead of one time. And then finding out when the second derivative is equal to 0 to find more things out about the graph. So it's a review of all of our techniques of taking the derivative and then applying what we're learning about, derivatives representing the how our graph increases or decreases, finding max mins. We can put all this together to help us figure out how the graph looks of a difficult function that we wouldn't know without a calculator, graphing calculator, or plotting points. Okay, so I think that's a good spot to stop. And then Thursday, if you have any questions over 5.2, we can go over that before we start on 5.3. Let me just turn off the video if I can. Real quick.